everybody. Help if I turn this on. For those of you that don't know me, I'm Marcus Noble. I'm currently a platform engineer at a company called Giant Swarm, where I work on release engineering, CI/CD infrastructure, and more like general Kubernetes, like cross-provider stuff. Quite recently, I started running a monthly newsletter where I round up everything that's happening in the cloud-native world, like blog posts, new tools, some gossip, all that kind of thing. I'm a CNCF and a CVO ambassador, and at this point, I've now got about 7 to 8 years worth of experience with Kubernetes. I actually started off as a full-stack Node.js developer, where I was working in an e-commerce team for a global multinational, and I was tasked with like trying out this new Kubernetes thing to see if it would work for the team. Turns out it did. I worked building out this Kubernetes, 3 Kubernetes clusters for our ecom team, so a dev, staging, and production. I moved then into a more R&D role within the company to build out like best practices and tooling for teams all around the world, and then moved into more like platform engineering and operating clusters at scale for other customers and things like that. So over my time, I've kind of experienced different roles of Kubernetes and the way that different people use Kubernetes. So I've been an app developer deploying things to it, to actually like building out the controllers and working on the Kubernetes code base and things like that. So when I proposed this talk originally, I wanted to do an actual deep dive into everything about pods within Kubernetes. So I started writing it, putting my slides together, and I got to slide 100 and something. And I was like, I wonder how long this is going to take to do. So I did a quick run through, and it was over an hour. So buckle up. No, I then refactored it. I was like, okay, I can't cover everything. Let's talk about just the weird stuff, the things that kind of made me go, what? Why is it like that? The things that I wasn't aware of, the things that I learned basically while doing this deep dive. So let's start off very simple. What is a pod? Hopefully you're all familiar enough with Kubernetes to know what Kubernetes is-ish. Let's talk about what pod is, which is kind of a central part. This is from the official documentation. Pods are the smallest deployable unit of computing that you can create and manage in Kubernetes. So what I mean by this is it's the smallest deployable unit, as in this is the thing that wraps around our containers or our WASM functions or whatever. It's something that can run code. It's a wrapper around one or more of those, so at least one container or function, could be more, managed by the Kubernetes scheduler, and they're assigned to nodes at runtime. All the workloads running within a single pod share a Linux namespace, C groups, the same networking, things like that. So they're kind of like bundled together and have some cross communication. They're designed to be relatively ephemeral and disposable for the most part, and mostly immutable. So once you create a pod, there's only a few things that you can change on that pod without recreating it from scratch. So you can actually change the image, you can change active deadlines, tolerations, and as of 133, you can actually change resources. So you can give it more or less resources at runtime now, which is very, very nice. But really, it's much more than that. Too much to cover, in fact. As I said, I got over 100 slides. I hadn't finished, so we're not going to go all that. But let's talk about the interesting, weird, and surprising bits. And I'm going to start very simply with containers, because they are effectively the core. Without the containers, pods aren't going to do much. Kubernetes isn't going to do much. We wouldn't be here. So I want to talk about sidecar containers. So these are relatively new, let's say. They came in 129 as enabled by default. They were available before that as beta through the sidecar containers feature gate. Now, what is weird about these is they are disguised as init containers. So the way you define a sidecar container is you create an init container and you give it a restart policy of always. I don't know why. That's just the way they've decided to do it. This is restart policy on the container level, and not to be confused with restart policy that you can have on the pod level. This only has the one value, so you can only set it to always or just not exist. And if you do this, this means that the pod will start up as an init container and then continue running after all your init containers alongside your main workload containers as a sidecar. They support more things than a normal init container can support. So they have things like a readiness probe, for example, which is useful if you do want it to run alongside your main workload containers. whereas your init containers do not have this sort of thing. And they're also handled a bit more harshly than your workload containers. So they will be terminated much more aggressively than your application pods might do. So just be aware of that if you have anything like cleanup logic or like handling during your SIG terminations or whatever, that they may just be like killed off quicker than your main pods. But the idea is that they actually do stay around for the entire lifespan of your pod. So at the start all the way till the very end. Okay, let's move on to ephemeral containers. So these are amazing, right? These are designed for debugging. When things go wrong, you want a way of figuring out what is going wrong. And this is where ephemeral containers come into things. They can only be added via this special ephemeral containers handler. So you can't add them to a pod spec, like in your YAML. You have to use something like kubectl debug, that then behind the scenes use this special handler that kind of like injects this ephemeral container alongside your other containers within your pod. It's not supported on static pods, so you can't do this with like the API server pod, for example. And we'll talk about those a little bit more in a bit. And you can also target specific container process namespaces. So you can do the target container name property on your ephemeral pod, and you can then start debugging that container's specific environment and figuring out what's going on there. Because these are kind of a weird pseudo container-ish sort of thing, there's no support for things like ports and probes and resources and life cycles. So they are really just a limited thing where you can drop in, get an executable shell where you can like poke around at things and then come out of it. And then they'll just kind of like sit there on your pod until the pod gets deleted and recreated. Pause containers. So these are very interesting. Now, I can guarantee if you've used Kubernetes, you have used these, whether you know it or not. They are in every single pod. The idea of the pause container is effectively like a bootstrap for your pod. It's what is responsible for setting up that Linux namespace, the C groups, those kind of things. And you can kind of think of it as like a parent container. The idea is that this pause container will remain even if your containers crash. So as long as this container still exists, your C group still exists, your namespace still exists, all that kind of thing. So it makes sure that that will always remain for you. If this crashes, your pod's pretty bad. You will not see the pause container if you do like a kubectl against the API server. It's invisible, but you can see it if you go onto the nodes directly and have a look at the running containers. So for example, if you're using containerd, you can use this little command here and it'll spit out. Here you can see I'm using a custom pause container in our Giant Swarm product, but you'll normally just see like a Google-based one or whatever it is. So they're relatively interesting. What is interesting is, in the official Kubernetes documentation, I found one page that referenced these, and it was on the documentation about Windows containers, and that was it. Don't know why. Let's move on to images. There's some fun things to talk about with images. So I want to talk very quickly about the image pull policy. So this is what instructs the kubelet as to whether to go and fetch a container image from your remote repository or whatever. And there are three values that this can have. There's if not present, always, and never. Now, if not present, we'll fetch the image from your container registry if it doesn't find it already on the node. Now, this is the default that's used if you specify your image using a tag or a char that is not latest. Always, it will always go and fetch the image. This is what will be the default if your tag for your image is latest, or if you omit it, which implicitly means latest. Now, what's interesting about this is that doesn't always mean that it will always download it from the registry. What it'll actually do, it'll query the registry for the layer chars and see if it has those layer chars on your node. If it does, great, because we know that they don't change. So we don't have to waste the bandwidth of downloading those. If it doesn't find all of those chars, then it will go and download it from the registry. And then, I need to stop doing that. And then never is, you got to figure out where the image comes from yourself. You've got to load it onto the node yourself through some means, whatever that may be. It will not even try and download it from anywhere. It just has to exist. Now, I've talked a little bit about image tags, and I want to talk about char-based image tags. So these are where you use the commit char, or the build char, sorry, of the image rather than using like v.1.25.1. This is recommended best practice because the SHA cannot change. It will always refer to the same built image, and that is good for security because it means that we can't like sneakily slip in some vulnerability at a later date and republish it as the same tag. Now, what is interesting here is if you specify a SHA and a tag, the tag is meaningless. So in this example I've got here for Nginx, that SHA is not 125.1. That points to another tag. And Kubernetes, kubelet, whatever, just completely ignores the bit before the SHA and will only use the SHA. So if you are using both of these, I recommend make sure that your tooling that updates them both in parallel so that at least your humans that are reading this know what version it is you're running, as does the computer. Runtime class. So this allows you to have different runtimes within a single cluster. So this is things like this is your container runtime interface, your CRI. It will default to whatever is configured on the node that workload is running on. So this may be container D, this may be CRIO like we see here. And if you want to use a different one, it has to be a runtime class that exists, which is what we can see on the bottom here. So there's a resource that we define within our cluster. And there are two properties that we can specify on here that are important. There is the scheduling, which allows us to say which nodes this runtime class is available on. So we may only have like one of our node pools that has cryo, another node pool may have container D, and then if we label those nodes with a specific thing, we can make sure that the correct ones are used on the correct nodes. And then you've got the handler, which tells the application, basically, the binary that we're going to run. Now, it's not very often that you will see like containerd and cryo used in the same cluster. That's a little bit weird, but where you will see this is with WebAssembly. So this is how you will have WebAssembly within your cluster as well as your normal image containers. So you will specify, for example, here a WASM Edge runtime class, and then I can reference that in my pod and run a WASM function rather than a Docker container or whatever. Now, so we're going to talk about static pods. So static pods are very interesting. These are actually managed directly by the kubelet on a node, not by the API server. And these are defined as static manifest files, either as a file on disk, a YAML file on disk, where you specify it with the pod manifest path flag, or you can reference a URL to go and fetch that static manifest from. I don't know why you'd want that, because that just sounds scary to me, but if you know of a legitimate use case for getting a static pod from a web server, I'd love to know. The kubelet manages these automatically, and for these static pods, it actually creates what's called a mirror pod. So a mirror pod is what you will see when you do a kube control get pods. So when you see kube control get pods and it's got the kube API server pod, that is actually a mirror pod of the static pod that is created by kubelet. It is a read-only view of that pod, because it is not managed by Kubernetes itself, it's managed by the kubelet. And each of them will get appended the name of the node that they are running on. So for example, you may see here, I've got kube scheduler, and then it's on control plane 1, because that's the name of the node that it's running on. Because they are managed by the kubelet, they cannot reference other Kubernetes resources. So you cannot reference config maps, you cannot reference persistent volume claims and all that kind of thing. It's just a pod. You can reference like some host paths and things like that, so you will see that with the API server, but that's about it. And the kubelet will watch this directory, and when there are changes made or things are added or removed, it manages creating or updating those pods. So even if in the API server you do a kube control delete pod on one of these, it looks like it deleted, and then it immediately appears again because it's just a read-only pod. That's it. Kubelet is dealing with it itself. Lifecycle hooks. So this is how we kind of hook into our lifecycle of our pods. These are guaranteed to trigger at least once, but they may trigger more than once, so kind of be careful of that. I don't know in what scenarios they do trigger multiple times, but this is what the document very clearly says. And there are two that I want to talk about. So there's a post start. So this will run immediately after the container is created, but is not guaranteed to run before or after the container's entry point. So if you are relying on something to have happened within your container, you need to have some way of being able to check that. These are good for kind of like initializing things. So the example I've got here on the right is from a Cilium pod that sets up some IP tables configuration when the pod starts up. The other one is pre-stop. So this runs immediately before the pod is terminated. So when you do, you're scaling down a deployment, you're deleting a pod, whatever, this will happen. So here, this is an example's got an uninstalling script, but I've used this myself in doing like backups of databases that I want to make, or when my pod's going down, I want to make sure that I've copied over some things to a network drive or something like that. And there are two mechanisms that you can use here. There's exec, which allows you to run some code within your container. So, whatever binary you want to run has to exist within the container environment, but it means that you can run like scripts like we see here. Or there's HTTP GET. This allows the API server to call one of the HTTP ports in your container and like trigger something. So you may see this sometimes in the post start where it'll like trigger a generate cache endpoint within your container, so it like pre-populates a bunch of stuff or something like that. Conditions and readiness gates. So these are similar-ish sort of thing where we're looking at the state of our pod and whether it's ready, running, and that kind of thing. So you've probably come across conditions while working with Kubernetes. They're on a lot of resources. With pods, the kubelet manages these, and you will generally see one of these conditions, or multiple of these conditions. So this pod schedule, this is when it has been given a specific node that it's going to run on. Pod ready to start containers, this is currently a beta feature, I think it's still beta feature. This is when the pod sandbox has been created, so this is like the networking and stuff. Container ready is when all the containers within the pod are in a ready state. Initialized is after that, and then all of the init containers have completed. And then ready is when we're on to our running of our main workloads. And then each of these has, or optionally has, two properties. There's either reason, which is a machine-readable code, or aimed to be a machine-readable code, and then message, which is meant to be the human-readable alternative to that. And these are what you'd use for like debugging to figure out what's going on. The reason I want to talk about this is because I want to talk about readiness gates. So these are very rarely used, I've found, at least in my experience. And these are a way of creating custom conditions on your resources. So we're going to talk about them here with pods. These rely on an external application, either within your cluster or externally, wherever, that will manage this. And the way that you use these is you define this readiness gate condition type, and this is just like a string, an identifier. And then that becomes the type for the conditions, and it defaults to false, and then your external controller is responsible for updating that to true at some point. And this then is built into your conditions, and you can use this to make sure whether things are ready or not. Now, a good example of this is from the AWS load balancer controller, where it supports this. It optionally supports this when you're using ALBs and NLBs, so it makes sure that the pod is not considered ready until the associated load balancer is created and ready to serve traffic to that pod.
Can this change back to false if something goes wrong?
Yes. Config. So I'm going to talk about environment variables first. One thing I was quite surprised of is you can actually have dynamic environment variables defined that reference other environment variables. So here we've got a static, a hard-coded one that is world, and then we've got a greeting that's hello, and then references the other environment variable name. Now this example's useless, generally, because you just want to put world in there. But when you use this with some other examples, it can be quite useful, and we'll kind of come on to that very quickly. So the downward API allows you to populate environment variables based on like status or spec from Kubernetes. So you can get things from the metadata. So for example, the pod name, which is usually a dynamically generated name which has a unique suffix on the end, which is then its DNS name, which you may need within your application. You can reference things on the spec, so for example, the node name, so knowing the node that it's got scheduled on. Things from the status, so finding out the pod's IP address, and also things from the limits, so we can find out what our memory limit has been defined as on the pod. So for example, if you're using a Java application, you may use this to set your maximum amount of memory that the Java application can use. And then you could imagine how these could be used in combination with the dynamic environment variable to have more complex environment variables that you're setting up that then reference these other ones. Cool. Let's move on to volumes. So this annoys me so much. When you reference a config map and a secret as a volume, with a config map, it's config map.name. With a secret, it's secret.secretName. I have to look this up every time, and every time I cringe inside, and I hate it so much. I really wish that somebody just bring in secret.name. Leave the secret name there for backwards compatibility. I just want them the same. It annoys me every time. And that's all I wanted to say about that. You can also use the downward API with volumes. So as well as having them populate environment variables, you can have them populate files. So a useful one with this is like for the labels or annotations, you can have those as files on your disk that you can then reference, and they would then get kind of populated. You can then use in your application however you need. But it has all the same sort of like spec and status that you can get else in your environment variables as well. Empty.dir you've probably used at some point. This allows you to have like a volume that you can use within your application to do stuff. What you might not know is there are different mediums you can use here. So by default, it'll actually create a space on disk, on the node's disk, but you can actually set this to do an in-memory volume. Make sure you have enough memory, because this could then like take memory away from other pods on the node. But if you are using memory, I recommend setting size limit, which allows it to have a hard limit that you can fill up. So here we're setting that we can't have any more than 500 megabytes of space within our empty.dir. But you can also have this for your on-disk versions as well. Projected is one that I'd not come across before, but turns out is actually used quite regularly. This is a way of kind of like merging together different volumes into a single volume. All right, so the example I've got here is I want to merge together two config maps that I've got into a single volume mount within my pod. So I've got a config map that has like an index.html. Let's just ignore how bad that is as a practice. And I've got another config map that has multiple error pages in them, each as different keys. And I just want those all in my Nginx directory, right? So I use a projected, it becomes one volume, and I mount it into one volume mount location. Wonderful. Come on. And then image. So this is alpha, it was in 31, beta as of 33, it's still disabled by default, but this allows you to mount an OCI image as a volume. It's handled in the same sort of way as your container images in terms of like secrets handling and how it's pulled and pull policy and all that kind of thing. But what's useful with this is because a lot more things these days are being packaged as OCI artifacts, so it's quite big in the AI space where we see models packaged as AI artifacts and things like that. It means you can just reference them directly as a volume that then gets mounted in. You don't need to have like them downloaded into another volume source that then gets mounted. You can just mount the OCI directly. It's very nice. So this is going to be interesting when it gets used more widely. Right, scheduling, and we're going to talk about resource allocation. And I'm going to very quickly talk about this because there's a lot I could talk about here and I'm not an expert, so we're going to talk about the weird things. So you may know about like requests and limits. Requests is the minimum amount of resources that a node has to have for your pod to get scheduled on it, and limits is like the hard limit of if I go over this, stop me running. With limits, it's handled slightly differently between CPU and memory. CPU, if you hit the limit, you get throttled, so your pod continues running, but it's not getting as many CPU cycles, it's kind of slowed down. Whereas memory, if you hit it, your container is terminated with an out-of-memory termination. You've probably seen this, and then it gets restarted. Now, what's interesting about this is you can have custom resource type. You can create your own. Like, it's not just memory and CPU. So if you've done like GPU-based stuff, so you've done AI, model, machine learning, that kind of thing, you may have come across this where you can specify GPUs that you're allowed to access. You can request one GPU and limit one GPU. Now, in this specific example, you cannot specify requests without limits, and they must be the same, but this is kind of like a quirk of the NVIDIA GPU stuff. But you can build your own. Like if you have another resource type that you leverage within your environment, you can define that, and you can encode that into your resource requests and limits. What is interesting is pod limits and requests are calculated as the sum of all containers. From 132, there is a new alpha that's disabled by default. I haven't checked on the 133. I don't know what it is in that. But this allows you to do like pod level resource specifications. So this will allow you to say, for my entire pod, I can have 1 gig of memory and 1 CPU or whatever. So this means that even if I have like a bursty init container, that then isn't like skewing some of my results and things like that. It's quite useful. You can just define this once rather than every single container having to define it. Node assignment. I just want to talk about one thing about this, which was new to me, but probably not to some of you, which is topology spread constraints. So this is a way of balancing out your pods a bit more across the nodes that you have, especially if you have multiple node pools, so thinking like multiple availability zones and things like that within your cluster. These allow you to define what's called a skew. So this is the number of pods, the count of pods within one node pool zone compared to another. So how many pods different? So in the example here, there's like skew of 2, skew of 1. So that pod will want to go over there because it has a lower skew. This can be used in collaboration with things like affinity and that sort of thing to have much more complex node assignments and make sure things that rebalance a bit. These are only guaranteed at scheduling time, not at runtime. So if, for example, you scale down, this generally won't be taken into consideration. So you may scale down and become unskewed, or become skewed, whichever way around it is. So just be aware of that it's only at scheduling time usually. Now, I want to talk about DNS, which I'm sure is everybody's favorite topic. No, I don't. That's in the wrong place. I want to talk about, I thought I'd skip something. I want to talk about scheduling logic first. So I want to talk about priority and preemption. This is a way of defining the ordering of our pods and how important one pod is to another one. Now, you can create these things called priority classes within your cluster, and these have a value for them that's just an arbitrary number. The bigger the number, the more important. Smaller the number, the less important. And then your pod can reference this priority class, and it will be used to determine the ordering of scheduling. So if a pod with a higher priority class will get put ahead of the queue of ones with lower ones, and you're also able to specify this thing called a preemption policy on your priority class, which has the ability of telling the scheduler you can deschedule this pod in favor of a higher priority one. So if you've got a pod that you know is okay to shove out the way for your super high priority e-commerce front-end one that's going to make you a bunch of money, you can tell your priority class this pod can be deleted to if an important pod has to be scheduled onto this node. And that's where your preemption policy comes from, or comes into play. Multiple/alternative schedulers. Very quickly, is anybody in here using a scheduler other than the built-in Kubernetes one? Yeah, that's exactly what I thought. It's possible. You can have multiple as well if you want, and you can reference them. By default, if scheduler name is unset, it will use whatever the default is in Kubernetes, so your Kubernetes scheduler. If you set it, the Kubernetes scheduler goes, right, I'm not touching that. And your scheduler, whatever it is then responsible for setting the spec.node property on your pod. Once that is set, it is then the kubelet's job to pick up that pod, the kubelet's job on that node to pick up that pod and do stuff with it. I'd be very interested if anybody is running multiple schedulers. I don't know. I'd love to know that. So now we're going to talk about networking and talk about DNS because I know everybody loves this stuff. So I want to talk about DNS policy. And I very much want to talk about how the default is cluster first, not default. There is a property on your pod called DNS policy, and the default is not the value called default. Naming's hard, right? Okay, we all get this. Default actually means the default of the node. So once you know it, it kind of makes sense. And cluster first is, it matches everything against the cluster first and then goes out to whatever the node says. Fine. If you have host networking, you want to actually use cluster first with hostnet. So you actually deal with that a bit better. It actually does in-cluster stuff, then out-of-cluster. And if you want to be painful to yourself, I guess, do none, and then you have to define all the DNS yourself using DNS config. So when you set it to none, you then have to specify this property yourself, which tells it where the name server is. So this is a list of up to 3 IP addresses of DNS servers. Optionally, the searches, which is a max of 32, which is your DNS search domains, and then options, which is just a key value pair of additional DNS options that you can have, with the value being optional, as you can see here. And that config effectively becomes this resolve.conf within your pod. Yeah, that's not fun. And that's everything I wanted to go through. I'm out of time. So hopefully there was some stuff in there that's interesting. If you want the slides, it's at the top. If you have any feedback, any comments, this is the first time I'm doing this, so there's this little thing you can fill out here. It's like 4 questions, super quick, like 1 to 5. I'd love to know what you think, how I can improve it, things that you might think should be included. And I'm about during the break if you want to come and chat with me about any of the weird stuff. So thank you.